everyone, and welcome to NVIDIA's GPU Technology Theater. Before we get started, just a reminder, we're recording all of these, and it'll be posted on our event site, nvidia.com/SC17. Also, if you enjoy this talk, we have the GTC GPU Technology Conference in San Jose, and this is just a sample of the kind of talks that we'll have, and there's a 20% discount on the postcards on the benches. So check that out and check out our website for more information. So I'd like to introduce our next speaker, Chris Gottbrath from NVIDIA.
Hello, everyone. Oh, wow, okay. I'll calibrate my enthusiasm appropriately here. Hi, everyone. I'm Chris Gottbrath. I'm a product manager for TensorRT, which is our inference, programmable inference accelerator that we use in deep learning. I want to talk to you guys a little bit about the role that deep learning and inference may play in HPC and is starting to play in HPC, and a little bit more about how we do inferencing at NVIDIA and how you can benefit from it. So, okay. What is inferencing in general is a valid question to start out a talk on inferencing at SC. So inferencing is is basically inferring from some data some result, and we use that term in deep learning. Alternatives are scoring and things like that to refer to when we've trained a neural network to do something. When we ask it a question, when we actually challenge it to give us an answer, we say we're inferencing with that trained neural network. So when we talk about inferencing in HPC, we're going to train some neural network to do some function, and then that's when we're going to use it. When we use it, we're doing inference. So basically, inferencing is using deep learning. So if you are interested in deep learning, if you think you have problems that can potentially be accelerated with deep learning, you're going to ultimately be using inference. You're going to be ultimately doing inference because you're going to use whatever you build, assuming it's successful. So how can So we should probably start with some canonical examples of how we use deep learning. Everyone is probably already using deep learning if you use, say, Facebook or Snapchat or any social media service. All of those big social media companies are using deep learning to help decide what stories should appear in your news feed. Or when you do a search on Google, at least a little bit of the Google rankings is due to neural networks doing inference on your query that have been trained with the accumulated knowledge that we've all put up in the internet. So we're already using. You guys are already using deep learning. Are already doing inference. We know deep learning is really good at basically recognizing patterns, classifying things, and in some cases it can be successful for doing regression. So looking at some pattern and pulling out some number or set of numbers. Now that actually could be pretty useful to scientists, right? We have physical systems. We might want to know things about those physical systems. Maybe we have an image coming into a radio telescope, and we'd like to know something about the object that's looking at. Now, we have all kinds of traditional techniques, and there's nothing wrong with those techniques, but there are, in some cases, really great advantages to using deep learning. So an example of how you might use deep learning, a workflow for deep learning in HPC is you might have a simulation. So I should step back a little bit. In deep learning, it thrives on data. So you cannot really use deep learning if you have 1,000 of something and you want to train the neural network to recognize. It's not usually enough data. You need tens of thousands or hundreds of thousands of the input that you're going to use to train the neural network to recognize whatever pattern it is that you want it to recognize. The great thing is, all of us here in HPC, we are swimming in data. We have gobs of data. We have too much data to know what to do with. So we're actually in a really, really good position. Almost every simulation produces enough data that you could, depending on what question you want to ask, you probably have enough data coming out of whatever simulation you're working on or your colleagues are working with to train a neural network to do something interesting. Right? Like you already have the big data that in other domains and in other places where people want to do neural networks, they're pulling their hair out trying to figure out where they can get enough data to train the neural network. You guys are already sitting on top of that. Anyways, you start with your simulation. You decide what bit of data that the simulation is creating you care about that's going to be the input to your function Basically, at the end of the day, a neural network is a function that takes some inputs and gives you some answer, right? And ultimately, it's about deciding what's enough data to train this sort of abstract feature recognizing machine to recognize the pattern. Anyways, you decide what data you want out of your simulation. You feed that into a training system. And I'm not going to talk about training too much here. I'll talk a little bit about it, but not too much. And then you validate that you've trained a neural network that does recognize whatever pattern you're looking for. And I would recommend you'll take some of the data that comes out of the simulation and use that to regression test, but you also probably want to bring some data in from outside. You want to check this against something that's other than that simulation. Anyways, hopefully, and there's probably a feedback loop here, because you probably don't do it right the first time. You probably decide, oh, well, I need to amplify my sample data with something additionally, and you go back. But ultimately, when you're done with that, you can do, you now have a function that can look at whatever the kind of data is that you've trained it on, coming out of your simulation, and hopefully the real world, that can then give you, it can infer, can give you an answer. And that's the inference side of things. And probably you'll learn some lessons from that process. You'll probably feed back into the simulation or into the training process. Ultimately, at the end of the day, you get some insights out of this process. Okay, that's all very abstract. That's the sort of abstract flow of how you can take the data you guys are sitting on top of, the wealth of data you guys are sitting on top of. What are some things that people have already done using this kind of flow? Not exactly this flow in all these cases, but in this kind of flow. So the LIGO, everyone's probably heard of LIGO. Some of these guys won the Nobel Prize this year for detecting black hole mergers. The LIGO signal processing was sped up, I think, 5,000 times faster by using deep learning. Doing general relativistic simulations from first principles in using numerical methods is really hard. But there's patterns there. Those patterns can be used to train a neural network. The network can then recognize those patterns and can identify them. You probably want to, after they detected things, they went back and simulated it the right way to validate the results and really make sure the numbers were right. But you can do that first detection really quickly using a neural network. That's vital because they have data coming in all the time. Same thing for drug discovery, for astrophysics. Fusion. Similarly, you have data coming out of the test reactor. How are you going to adjust the magnetic field lines to keep everything stable? That's a problem you have to get the answer right away. Like there's a numerical solution that might take a few hours. That's interesting, but when you want to use it, you want an answer right away. So you want something like deep learning. And maybe the answer doesn't have to be 100% accurate. It has to be right enough to adjust the right magnetic field in the right direction to keep the bottle from collapsing. So there are already some good examples. Talk to folks around here at the booth if you'd like more detail about some of those. These are all real case studies that we've developed over the last couple of years. Let's step back and look at this flow a little bit more. So you have your source data set. You curate that data set. You label it. So this in the HPC, your source data set will be your model. And you're curating your data set is choosing, well, what parameters out of this model do I want to use to train? You do training, and a lot of what you would come and learn if you come to GTC is about the training of neural networks. Right? There's some art and science to choosing exactly which framework, exactly what model structure to use, to the process of iterating. So basically, if you haven't heard this before, basically training is you start with a really dumb network. It's got basically random weights. It tries to guess from the data what the right answer is. It almost always gets it wrong. When it gets it wrong, there's this process of back propagation where you basically adjust it, you nudge it. If you guessed a little differently in this direction, it would have been better. And then you do that over and over and over and over and over again. The key to deep learning is this repetition, having enough compute to be able to adjust in tiny little increments the neural network to make it just a little bit more accurate. And then enough data that you can do that in a way that's generalizable. So again, you guys are sitting on top of huge data, so that should be possible in your case. And then when you get to inference, you've already trained the neural network. You already have a neural network that has just the right parameters. Hundreds of thousands of parameters have been tuned by this rigorous process. Here, you validated that it is actually giving the right answers. Then you want to deploy it. And that's where TensorRT comes in. When you're training, you're really concerned with accuracy and convergence and things like that. When you're deploying, you want lowest latency, because again, you're going to be using this to be the first mechanism that's sampling and determining whether data coming off of a big detector is worth keeping or not, or this is in the loop adjusting the magnetic field lines on or magnetic field strengths on a tokamak reactor. You care about latency. Accuracy, of course, you still want it to get the right answer. It's still doing the same math, so you're still going to have accuracy, and of course efficiency. A lot of times, this kind of depends on the use case, but if you're using this in a some sort of an edge case, a lot of times you don't have a lot of power there, so you want to be power efficient. And then throughput. So these are the kinds of things that the software product that I work on, TensorRT, is designed to deliver. So it takes a trained neural network, and it gives you those things. Ultimately, so that you can get for example, a microservice or a function inside your experimental design. Okay, so that's kind of where TensorRT fits in the life cycle. What is it? It is an optimizer and a runtime. Again, we call it a programmable inference accelerator, but it really breaks down to an optimizer that takes neural networks trained in a wide range of different frameworks. And these may or may not be familiar names here at SC, but if you go to one of the deep learning conferences, everyone's got their favorite training framework that they love, and all kinds of reasons why all the other training frameworks aren't quite as good. It's kind of like Emacs and VI. So everyone's got a lot of different training frameworks. Ultimately, they all do the same thing. They nudge those weights, we call them weights, the parameters in a neural network, to be slightly better during the training process. Ultimately, we take the output of that, we optimize that, and then TensorRT is a runtime which allows us to apply that neural network to a wide range of different GPUs. All the way from the V100, which you guys just heard about if you were here earlier in Stephen's talk, down to our automotive drive PX2, or our hyperscale, I think it's 75 watt Tesla P4, or I think I think it's like 15 or 20 watt Jetson TX2. So neural networks can be optimized for different basically power envelopes using TensorRT. Again, you start with a trained neural network for TensorRT. These slides are sort of progressively zooming more and more into your workflow and what you would actually do with TensorRT. The idea here is you start with a trained neural network, use any other frameworks that you want. TensorRT applies 5 different optimizations to that briefly, and I have some backup slides so I can talk in detail about any of these if you'd like. But briefly, we do weight reduction. So you usually train in a high precision, because you really are making these tiny adjustments to the weights. But once you've trained the neural network, now it's looking at kind of macroscopic patterns, and we found in lots of cases you can use FP16 or even int8 and still reproduce the numerical accuracy of the overall network. It's amazing, actually. It's an amazing result. Layer and tensor fusion. So when you're doing the training, you care about generality and debuggability and understandability by a data scientist of what the neural network is doing. So you use very atomic little operations or layers. Once you're in inference, you want an engine. You want something that's just optimized. So we find lots of opportunities to fuse those different operations together into single computational nuggets, which can run on the GPU. We call them kernels, and it's better to have a fused kernel that does the work of 2 or 3 operators than dispatch a separate operation under a separate function. We also do auto-tuning. We do a very exhaustive search of parameter space to find just the best kernel to execute any given set of fused layers. We have some very slick pipelining that is used to make sure that if multiple GPU tasks can run efficiently and concurrently on the same GPU. And we also have very efficient use of memory. So a lot of these things are, these are production kinds of things. Again, you already have your trained neural network. You want it to run fast. So TensorRT is applying a bunch of different kinds of optimizations that really make sure that neural network is going to run efficiently and robustly on the GPU, whether it's a tiny little GPU like a Jetson or an awesomely powerful GPU like V100. Okay, so that all probably sounded good, but we're all computer scientists and engineers probably in this crowd. So let's look at some actual numbers. So I've got two different use cases, and we're talking deep learning here, so that my two use cases are drawn from different kinds of data. So they're kind of different network architectures. The left one here is image data. So we're doing image classification. This is kind of, this was the real breakout moment for deep learning, was when we figured out that we could train neural networks to recognize objects better than humans. They can look at an image and recognize it better than you and I can, what that object is. So this use case is really at the heart of deep learning today. We're using ResNet. It's a very popular kind of reference network. There are bigger networks, there are smaller networks. This one's a pretty good size, pretty high accuracy network. We're trying to, the use case we have in mind for this graph is you want to put this in a microservice on the web, or in something that's going to be very responsive to the user. So there's an established 7 millisecond target. We want to be able to do this recognition in 7 milliseconds. We can do a bunch of them at a time. The user never has to wait. It's just immediate. And we're going to look at that on the CPU. We're going to look at that on our V100 using TensorFlow, which is one of these training frameworks. So good. And then on 2 of our different GPUs. The figure of merit we're going to use here is our throughput. How many of these can we do at the same time? So the idea here, we're kind of thinking of like a cloud data center. You have a stream of all the images being taken all over a city, and you on the security cameras all over a city. You want to process them, right? But it could be Snapchat photos. It could be anything, right? So higher is better, basically. You want efficiency. So CPU can do not terrible, 140. This is a pretty good recent Intel GPU. TensorFlow on a GPU runs much better, right? You can get almost three times as many images per second. And this is, again, using a framework software that's really designed for the training. So it's not applying those 5 optimizations I talked about. Applying those 5 optimizations, we go from here to here. So much faster. Many more images per second. And we're just kind of showing at the lower power point, if you don't have 300 or 350 watts in your data center to put a V100, you can put a P4 in. Still pretty darn fast. Over here, we're looking at a different problem. Now we're looking at translation, so textual data. You're like, oh, my data doesn't look very much like a bunch of images. My data looks like text that I want to process. There's all kinds of complexities in natural languages. There's all kinds of, the meaning of the sentence might be determined by the last word, and that might change how you interpret all the other words that came before. I mean, it's a hard problem, and you might be translating between different languages, so the orders are different. There's not an exact match between the words that are used in different languages. It's a fundamentally really, really hard problem. Same kind of graph. We're doing sentences per second now. CPU only, using Torch. We get 4 sentences at a time, or per second. V100, using, again, the same training framework, does a much more respectable 25 sentences per second. And again, same hardware. Same hardware, same network. Now we're applying TensorRT, which is our optimizations for inference. We slam, we just do a lot more sentences per second. And again, at a lower power point, we can still do a very respectable 65 sentences per second. Now, there's another parameter going on here, and I'd love to talk to anybody who would like to dig into this, but the another parameter here is the latency. So we said we had a target of 7 milliseconds here. So with the CPU, we couldn't even hit that target. With TensorFlow, you can kind of just barely hit it. With TensorRT, actually, you can blow that away. If you do batch size of 1, this number, the bar wouldn't be as high, but the latency bar would be way down here. But if you have a 7 millisecond latency and you're dealing with a flood of images, don't do them one by one. Once you can beat that number, you up the batch size. You all would. So that's how we're calculating this. So we are comparing different batch sizes across here, and the text down here shows exactly what batch size we're looking at. Same argument over here. We start off with the CPU. It has a very kind of slow latency compared to what we can do with the GPU. And we show settings where we basically have the latency. We don't have a 7 millisecond number we can target there. Okay, the point of this is GPUs can do inference really fast. They're designed to do matrix multiplications. Basically, deep learning boils down to a bunch of matrix multiplications. So if we apply software that's really optimized for doing forward pass inference and squeeze out all the overheads through the process, we can get really awesome numbers out of modern GPUs. What does that mean to you? If you're building a data center to do this, or if you're thinking about how much of my big HPC center will I need to do to run my model, we get these kinds of things. So this I think again is using image recognition using ResNet 50, and we're saying 160 GPUs can be replaced with 8. Or sorry, 160 CPU servers could be replaced with 8. Oh, and by the way, you're melting a lot fewer glaciers with 3 kilowatts than 65 kilowatts. I know that's a big deal for HPC centers. If you're designing a center or you're advising people who are, you're thinking about the power use. None of us want to be bad citizens and just burning watts just to burn watts. Okay. I actually started off with some inference use cases from science, just so stepping back to some specifically TensorRT inference use cases. And unfortunately, I don't have any of those for the big science applications, but I do have some pretty interesting problem domains. So we have transportation with Uber. We have a sales brand recognition use case with SAP, and we have a human pose recognition there with Ridge. So I think the clock tells me I'm out of time. I have some backup slides I can go to into the details of the tech, but thank you very much for your attention and patience and for learning about TensorRT and inference.